If we observe the universe strictly through the lens of classical physics, space and time appear to be an independent, pre-existing container. But spectral geometry suggests a more complex structure. The universe operates as an active, continuous rendering process, projecting the localized reality we experience from a deeper layer of mathematical data. Logos field theory describes this mechanism as an Adelic decompression. Spacetime functions as an analytical interface, where a localized observer acts as a transceiver, decoding raw arithmetic structures into physical laws. We can trace this directly through the Chamseddine spectral action principle. In the large N limit, this infinite-dimensional operator trace reduces directly into local Euler-Lagrange equations, yielding the precise geodesic equation that dictates motion in general relativity. The localized, smooth trajectories we identify as moving matter are the semiclassical shadow of this underlying arithmetic compilation. The math compresses, and the physical path renders out. Spectral geometry reveals gravity as the geometric output of a mathematical rendering pipeline recalculating its data. Before it decompresses into a stable vacuum, the baseline state of the universe exists as an infinite-dimensional, chaotic broadcast of quantum operator fluctuations. This creates a structural tension. Microscopic reality is governed by non-commutative operator algebras and radical probability fluctuations, yet we perceive a smooth, continuous, and strictly local Riemannian geometry. The root mathematical object spanning this gap is the Dirac operator. It acts on the harmonic bundle of the system, containing the entirety of the universe's raw, uncompiled spectral data within its eigenvalues. Left on its own, this raw operator data is entirely chaotic. To generate the stable physical universe we inhabit, this mathematical noise must pass through a rigorous, scale-dependent filtering mechanism. To isolate a stable, macroscopically coherent spectrum, the rendering pipeline relies on Gaussian unitary ensemble, or GUE, filtering. This process systematically suppresses the high-frequency quantum noise that would otherwise tear spacetime apart. We can track exactly how this works by applying a generalized Lichner-Rowich formula to the squared Dirac operator. We separate the raw data into a Laplacian and an endomorphism field, and then evaluate the asymptotic heat kernel expansion. This reveals a sequence of geometric invariants, the Seeley-DeWitt coefficients, which dictate how space compiles. The leading order coefficient, a sub 0, scales as a quartic divergence. It represents the unconstrained, raw quantum noise density of the operator-algebraic spectrum. By applying the GUE filter to evaluate this as a flat ensemble average, the system pins down the deep, uncompiled bulk volume, effectively rendering the cosmological background vacuum energy. The second coefficient, A2, processes the first non-trivial structural information. It extracts the curvature scalar and the endomorphism field, decompressing the Einstein-Hilbert action into a continuous macroscopic metric tensor. By the time we reach the A4 coefficient, the high-frequency cutoff entirely decouples. This term provides the scale-invariant dynamic equations, locking the gauge field coupling constants to the newly formed gravitational constants. This chart visualizes the precise effect of the GUE filter on the raw spectral density. As the matrix dimension approaches infinity, the highly fluctuating chaotic microstates organically self-organize. The ensemble smooths out to form Wigner's semicircle law, creating a tightly bounded perimeter space. The smooth, continuous geometry observers perceive as empty space is the result of this high-frequency spectral cutoff. The filter forces the raw, chaotic math of the Dirac operator to average out to 0, leaving behind a stable manifold boundary. If the GUE filter perfectly smooths out quantum noise to create an empty vacuum, we must identify the mathematical origin of localized matter. How does a discrete physical object emerge from a continuous background? We approach this by injecting a compactly supported operator perturbation into the Dirac operator. This models a localized field fluctuation, like a highly energetic particle or a massive field excitation interacting with the vacuum. The outcome of this interaction is governed by the Bike-Benarouz-Péchet, or BBP, phase transition. This determines the exact threshold where an isolated interaction detaches from the background quantum C, dictated by a coupling strength parameter theta. This spectral cluster chart shows the subcritical phase, where theta is less than or equal to 1. The localized interaction is too weak. Its mathematical data remains trapped inside the collective quantum statistical fluctuations of the vacuum, governed by Tracy-Whittem edge scaling. The continuous render absorbs it completely, producing no macroscopic physical object. But when theta exceeds 1.0, the system enters the supercritical phase. The perturbation overpowers the background quantum noise. A single eigenvalue explicitly snaps out of the Wigner semicircle boundary and migrates to an isolated, stabilized location in the spectral landscape. This isolated spectral outlier is the exact mathematical seed of a discrete, localized geometric state. It has escaped the flat vacuum boundary. In this framework, mass and energy sources are spectral outliers, mathematical data points that successfully overpowered the vacuum noise to project their own independent coordinate. The extraction of an eigenvalue does not happen in isolation. Its presence immediately alters the underlying arithmetic configuration of the system, specifically changing the properties of the arithmetic variety at the infinite prime. This diagram outlines the regularized determinant shift. The local perturbation forces a non-zero variation in the analytic torsion component of the Quillen metric. The spectral geometry of the system has now been warped at the source level. To translate this arithmetic variance into the physics we observe, the pipeline executes the Grothendieck-Riemann-Roch theorem. The GRR pushforward takes the shifted spectral data from the algebraic family and decompresses it down onto the macroscopic base manifold. As the perturbed Chern character is pushed down to the base space, it forces the smooth macroscopic metric tensor to deform. It yields a localized curvature anomaly, a persistent gravitational potential well generated entirely by the local spectral shift. The unperturbed geodesic equation immediately absorbs the deformed metric into its perturbed Christoffel symbols. A classical path passing through this region must navigate the updated geometry, resulting in a severe deflection of its trajectory. This operator-algebraic pipeline acts as the mathematical foundation for the rules laid out in general relativity. Einstein's equations perfectly map the result, but the GRR pushforward reveals the computational mechanism causing it. Classical gravitational lensing is an observer's illusion. The local field interaction updated the operator data, and the continuous engine calculated a new arithmetic path. Operating an infinite-dimensional rendering pipeline introduces a massive structural hazard. If the baseline mass parameters drop to zero, the unconstrained spectral trace encounters severe infrared and ultraviolet mixing. The functional determinant should theoretically blow up into infinity, instantly collapsing the rendered universe. To survive this, the system relies on zeta function meromorphic regularization. It acts as an analytical shield, mathematically stripping away the infinities before they can project into the physical metric. This visualization models the complex S-plane. Rather than allowing the heat kernel trace to hit an ultraviolet divergence, the zeta function analytically continues the data into a meromorphic function. It maps the infinite, dangerous divergences strictly to manageable, simple poles dictated by the manifold's dimension. Because the gamma function naturally cancels poles at the origin, the value of the regularized determinant evaluated exactly at zero remains completely finite and stable. This protects the analytic torsion of the Quillen metric from infrared collapse. Without zeta regularization, scale invariance anomalies would destabilize the geometry of the manifold. This mathematical protection keeps the macro geometry of the model intact, preventing the geometric projection from collapsing into a singularity. One final vulnerability exists in the render. Non-Hermitian perturbations, such as an open thermodynamic system exchanging energy with a reservoir, can cause eigenvectors to lose their strict orthogonality. This introduces exceptional points, injecting imaginary components into the metric and causing paths to spontaneously decay. The mathematical defense against this geometric decay is the PT-symmetric constraint. By forcing the operator to commute with joint parity and time reversal symmetry, the system guarantees the spectral data remains completely real, despite asymmetric dissipation. However, at the tipping threshold of an exceptional point, the standard inner products used to calculate the physical state collapse entirely to zero. If left uncorrected, classical quantum probability tracking would instantly break down. To prevent this collapse, the system dynamically constructs the C operator. This metric redefining gauge transformation replaces the indefinite probability metric with a strictly positive definite inner product space. It restores perfect mutual orthogonality between the states, forcing the probability of the state vector to sum securely to 1.0. Through the GRR pushforward, the C operator eliminates all complex-valued singularities before they can reach the base space. It forces open, highly dissipative quantum interactions at the microscale to project upward exclusively as stable, unitary, and conservative macroscopic trajectories. Tracing this architecture from infinite-dimensional algebra down to a moving body, reality resolves into a continuous pipeline. First, GUE filtering takes the chaotic broadcast of the operator-algebraic spectrum and forces it into a flat background vacuum. Second, BBP phase transitions allow eigenvalues to break free, altering arithmetic torsion and triggering a GRR pushforward that projects localized mass. Finally, zeta regularization and C operators shield this data from infinities, ensuring the macroscopic shadow remains perfectly stable. Physical laws are the strictly filtered, decompressed outputs of these arithmetic rules executing in real time. Observing general relativity through spectral geometry resolves massive objects into streams of glowing mathematical data arrays. The solid matter and vast distances we perceive are simply how a localized transceiver decodes a continuous mathematical broadcast. Space is not bent by the mass inside of it. The container itself is the projection. A localized interaction updates the arithmetic compile, shifting the spectral data at the root. The universe recalculates, and the geometry we walk through is the result of that math rendering out.